I don't actually have experience on in that position. I've never been part of a search committee for that kind of thing, but I suspect that they are looking for people who are genuinely passionate about doing something there. But it's also good not to be so narrow. You got to acknowledge that you don't know what you like yet. You know, I mean, there are some people who have very specific preferences, and that's a different situation. And that can also work for you, but that can work against you too. I don't know, when I got to grad school, they told us that they brought us there not because of what we were interested in, but because of what they thought we could do. And that made us pretty angry. Because we kind of had particular interests. But anyway. Okay, so finally, let us begin with the real story arc of the course, all right? So I'm in chapter 1, so I posted these as lecture notes. This more or less mirrors, elementary differential geometry by Barrett O'Neill. I'm pretty sure I'm behind my schedule now, but that's okay. We'll take it one day at a time, and I may have to adjust the schedule, so hopefully not. Let me get to it. So notation is what I have to set here to start with. I'll try to be brief. So Rn, you guys know what Rn is, right? So here we have p-tuples, right? And we can define the sum. If we have point P to point Q, we talk about the I coordinate of it. It's Pi plus Qi. So you notice I'm using an upper index, right? Maybe you've used lower indices before. I'm using an upper index for the coordinate. Okay, that's not a power, that's like a label. So, for example, x in Rn, well, let's not say x, let's say p in Rn would tell us that p is equal to like p1, p2, pn, right? Now, I should also mention we could write that as, we can also write that as like, P1 times 1 with zeros. Like that, right? And so these are the so-called standard basis. This is E1. This is E2. This guy is En. Right? In other words, the point is the sum I equals 1 to n of P upper I, E lower I. So we can build any point from a sum of the standard basis, right? So what's a formula for the component of the, so comment. If we look at EI, right, and we calculate the jth component of that, what is the formula? The way it works is it's 1 if what? It's 1 if I is equal to j, and otherwise it's 0, right? That's what those are. Now, this thing I just wrote, 1 if I equals to j, 0 if I is not equal to j, this has a name. This is the so-called Kronecker delta, right? So a notation for this combinatorial device is Kronecker delta ij, like this. Now, some people would put the j index like upstairs rather than downstairs. I don't care. So I guess I should also mention, what's the other thing we define for Rn? Scalar multiplication, right? Like what's C times P equal to? Right? And those rules are what? Those are for all I. that defines addition and scalar multiplication. All right. Now, of course, I say we can either envision P as a point with the Cartesian coordinates P1 through Pn, or we can envision P as a vector emanating from the origin out to the point P, right? We always have this like freedom when we're thinking about in 3 dimensions, right? Is this the point x, y, z, right? And let me instead say the point P1, P2, P3. Old habits die hard. Right? Is it this point, or is it a vector? What do you think? Point or vector? Vector? Point or vector? Vector? Point or vector? Vector. Point or vector? Point or vector? Vector. I mean, there's not a right or wrong answer. The point is that you can think about this as either a point or as a vector. Now, a point, of course, I mean, sometimes I'll write a vector over it to emphasize I'm thinking of it as a directed line segment, right? But if you give me a triple of numbers, that does label, right, a particular point in space. Now, that is in one-to-one identification with vectors from the origin, right? But you don't have to make that identification if you really don't want to. But we do all the time in Calculus 3 especially. So anyway. But what if you were to talk about vectors at some other point? Because we'd like to do that. All right? So, I would say that when you make this correspondence between points and vectors in R3, you're really making a correspondence between points and vectors based at the origin, right? So there exists correspondence between points and vectors based at the origin, right? But we'd like to have a notation to talk about vectors based other places, right? Like, what if I don't anchor the vector at the origin? What if I anchor it somewhere else, right? And so that's what brings me to the following definition. TP, T sub P, Rn, is going to be P Cartesian product with Rn. All right. And what does that look like? That looks like P comma V such that V is in Rn. So we're just giving a notation to say, hey, this vector is based at the point P. All right? And the tangent, this is the tangent space. Tangent space to Rn at the point P. Now the tangent bundle what's the tangent bundle? Tangent bundle, is just big T Rn. What that's going to be is the union over P and Rn of these guys. Not sure. I think there's a typo there. There's a typo there. I don't need. Sorry about that, guys. I don't think I need that P there. A typo in the notes at the moment. Okay, so visually, you can think about this as, again, vectors based at the point P. And you can give TPRN a vector space structure, right? So what's the vector space structure? How do we give something a vector space structure? What do you got to do? You got to define how to add vectors and how to scalar multiply them, right? If you can do that and they satisfy the axioms of a vector space, you got a vector space, right? So you guys tell me, how are we going to add vectors? If I have PV and I want to add it to PW, what should the rule be geometrically? Can you? So like here's the point P, right? This is V, and this is W. What should, if we want to add those 2 points at the point P, what do? Do we do anything with P? If you think about it, we don't, right? We just add the vector parts. That's tip-to-tail vector addition is what it is. So the rule is just P, comma, V plus W. So the P, basically the P just rides along. And like same story for scalar multiplication, like that. And we can also talk about dot product and norm. Like, how would you take the dot product of two of these guys? Exactly, just ignore the P altogether and just do V dot W in the ordinary sense, right? The formula for that would be V transpose W. Here, my vectors in Rn are column vectors, all right? So how about the norm of the vector PW, PV? It's going to be the norm of V, right? So you're like, well, this is all kind of dumb. You're just saying the P just rides along. Yeah, that's what I'm saying. All right. So, and we can also talk about orthogonality of vectors. What would it mean for, let's say, PV, PW, and TPRN are perpendicular if what? What does it mean for two vectors to be perpendicular? It means their dot product is 0, right? But of course, that just means what? That means that V dot W is 0, right? Again, the P just rides along. Furthermore, I wonder if you guys saw this in linear. If we have S as a subset of Rn, right? Actually, sorry, I've forgotten my place here. Suppose S is a subset of the tangent space to P at Rn, right? So then I can ask the question, if that's a, you can define the perp, the so-called orthogonal complement. So what this is going to be is PW such that PW dot PV equal to 0 for all PV in S. Now, if you're like me, I'm starting to get really, really tired of writing the P. All right, so admittedly, when I've worked homework problems for this kind of thing in the past, sometimes I drop the P because I just get like tired of it. I just write a word, I write a sentence at the start of my problem. All of the vectors considered are based at a point P. And maybe the P is specifically like 1, 2, 3, or 4 or something for the problem. All right, let's look at an example here. Let's look at a specific example. I'd like to review a calculational technique that you may or may not have ever seen before. All right, so the idea of perpendicularity is important to us in this course. We're going to do things with that, all right? Maybe not quite in the way I'm about to do, but let's see here. So what I say in the notes is I say, okay, so if S plays the role of the tangent space to some object at some point P, then the perp we would identify as the normal space. So let's see here. What do I mean by that? So I think of, let's see, how can I say it this way? I think of the whole tangent space at Rn as like, it's sort of like this universal canvas on which you can draw other tangent objects, right? But if you had a subset of Rn, you could look at tangent vectors to that subset. And let's see, for example, all right, if I have a curve, right? I can take a point at the curve, like here, you know? Maybe that point is P. And that point P, I can think about like the velocity vector, right? So in this case, the tangent space to the curve at the point P is as the tangent line. So if this curve is alpha, let's say, then I would think about the tangent space. I really should stop writing. I'm not sure that I'm being consistent with the notation of my notes if I get too carried away here. I've got to give this a name. Let me call this thing a curve C, like C for curve. So the tangent space at P to the curve, to me, it would just be the span of, well, P comma V, if I'm going to be stick with this notation. So this, now I didn't tell you where this curve fits, right? What do you guys want to do? 2 dimensions, 3 dimensions? What do you want? You don't know? We'll go with n dimensions then. So this curve is in the box of Rn, right? In that case, the velocity vector is an n-dimensional vector, right? If you have a curve in R3, its velocity vector is 3-dimensional, so forth. So this then is a subset. I'm thinking of this as being like that S that I wrote about over there. You know, it's a subset of TPRN. And so what would the perp to S be? This is the normal space, what's called the normal space. Normal space to C at P. For example, if we made n equals to 2, right, what would it be? N equals to 2, you get a normal line. N equals to 3, you get a normal what? let me be more explicit, all right? Let me, would you guys want to go with n equals 2 or n equals 3? We'd go either way. 2? All right, cool. So let's suppose alpha of t is equal to, like, let's say t and t squared. So this is a parameterization of the curve, right? And let's let p equal to alpha of 1 for the sake of discussion, right? Where does this curve go through at 1? T equal to 1, we're at what? 1, 1, right? So what's alpha prime of 1? We get what? We get 1 and 2, right? I'm reverting to my Calc 3 notation. I write angle brackets for vectors to emphasize their vectors, but see, if I'm sticking with my dogmatic new notation, I would say, okay, so the v I have in mind is p, comma this vector 1, 2, right? Or you could write 1, 1, comma 1, 2 if you really wanted to. I mean, anyway. All right, so great. The tangent line, let's look at it here. I mean, I can graph this thing. What is this? X equals to t, y equals to t squared. That's a, let me write it, let me say it in a different way. Y equals x squared is a parabola. This is a parabola. I put x equal to t, so. So right there, the tangent vector goes in the 1, 2 direction, 1 over 2 up, right? So the tangent line, come on. This is why we can't have nice things. I should have drawn the tangent line first and then drawn the curve afterwards. Well, anyway, there's my attempt at drawing the tangent line. So this is the tangent space to P of C, at least. And I say that, but the truth of the matter is, before too long, we're going to become more abstract. But this is the first thing I would think of as the tangent space, is literally the point set, which is the tangent line. Like that's, but I'm thinking of it not really as the point set as much as I'm thinking of it as the vectors which are attached at that point, you know? It's really the set of vectors that are based at this point and point in the tangential direction. What's the normal space here? What's TPC perp? That would be P comma, let me just say AB for a generic vector, right? Such that, well, I'm getting tired of the, I'm getting very tired of the P. Yeah, I mean, that's what it, that has to be 0, right? What does that give us? We get A plus 2B equal to 0, right? So that tells me that oh man, I got, you know, eventually I will learn to never pick up those erasers because they don't do what they're supposed to do. In contrast, my eraser, sure, it's magical. So look, what this is then is P comma what? We could solve this for A. A is equal to minus 2B, right? So you've got minus 2B, B, such that B is the real. So we can rewrite that as P, Cartesian product with the span of minus 2, 1. So like a span, do you guys know what span is? You didn't talk about span in linear algebra? You did not talk about span in linear algebra. Okay, so I have one vote for talked about but forgot, and I will allow it. That's good. So like generically speaking, if we have a finite set of vectors, let's say v1, v2, vn, and please jump in. Like if I say something like that and it doesn't make sense, just like interrupt me. Like if you don't understand, probably everybody else doesn't either, right? So all this means is the set of all linear combinations of those vectors. So it's like c1v1 plus c2v2 plus cn/vn. So basically you're creating a linear space which has all of those vectors v in it and all possible scalar multiples of them and sums. It's a way to build vector spaces given a particular set of vectors. I mean, the vectors are usually called the generating set. If these vectors are linearly independent, then they're a basis, and this is an n-dimensional vector space. If there's a linear dependence, it might be smaller. If you have one vector, like down here, see this I could rewrite as b times minus 2, 1. It's a scalar multiple of this. That's what the span of one vector means. It's just all possible scalar multiples of this vector. That's why I write span. And annoyingly, I've attached the p because we're thinking about these stupid things based at the vector at the point p. Okay? So like I can draw that. I can draw that back over here, right? That's also it's a normal line. In what direction does it go? Over 2, up 1, right? So I sometimes would call that the normal space at P to C. The normal space at P to C is the, the perp and the normal space. The tangent space and the normal space, they are complementary. If you put both of them together, they give you everything, right? So like it's a theorem of linear algebra, essentially, that the tangent space to P at S in direct sum with the tangent space to P at S perp is going to give you, can I erase my span? Okay. It gives you everything. Now, you guys probably didn't, do you know what this plus circle means? This is, of course, for S, a subset of Rn. I just used S in a different fashion than I did previously. I had taken S to be a subset of the tangent space. Now I'm supposing that S is a subset of the space itself. I'm using S in a different way here. That kind of begs the question, how do we find the tangent space to a given subset of the space, right? We just did it without flinching for the curve, right? We differentiated the curve and its velocity vector gave us the tangent space. How would we find the tangent space to like a surface? We find a parameterization for the space, and then we look at the derivatives of the parameterization in the coordinate directions, like we did in Calc 3, like the xu and the xv. Remember the cross product of those gave us the normal. So we could do something like that. Okay, anyway, I'm getting ahead of the story. But listen, this plus circle, what that means is that, first of all, you can add together these two spaces and get anything over here. And the other thing the plus circle means is that the intersection of those two things is just the zero vector.
Oh, sorry. The plus circle means what again?
Plus circle is direct sum. And here I mean internal direct sum. So we say that V is equal to the direct sum of two other like subspaces. So suppose V is a vector space, right? V is the direct sum of subspaces V1 and V2. The definition of that is if and only if V is equal to V1 plus V2 and V1 intersect V2 is just the zero space. This is called a direct sum decomposition of the vector space V. The tangent space and the normal space for some object in Rn, be it a curve, a surface, or a volume, whatever, it gives us a direct sum decomposition. But it's also geometrically interesting because the one part is the tangent space and the other part is the normal space. Let's see if I can, I think one-dimensional object is kind of like hard to track. I think it might be healthier if we did a four-dimensional example and a surface in it. Let's find the tangent space to a four-dimensional thing and a surface while we're on this kick here. If I can find my eraser. So, this begs a question, right? I suppose what I'm saying is I want an example to show you guys to get the ball rolling in here, because what I'm doing at the moment is trying to give you some kind of sort of intuitive picture of what I mean by tangent space and normal space for specific objects, because we're about to take these things and abstract them. So before I do that, I just want to do a little bit of concrete examples.
So, like in Cal 3, we did normal vector and tangent vectors.
Right.
So every time you like increase the vector space, you just get a surface, or then you get like so like if you went to 4 space, the tangent vector would be a surface, and the normal vector would also be a surface. Is that what we're doing?
Well, vectors are always vectors, but but I mean, things will change, yes. I guess my question is, let's just talk about R3 for a second. How do you describe a surface?
It's like a range of points.
A range of points, right? Euclid would say it was something that has in this thing I was reading from you, there's, like, we could go back to Euclid and see what he said, right? Which I think is kind of fun. A surface is that which has length and breadth only. Well, now it's clear, right? But in terms of analytic geometry, we have two choices, right? So I'll start you out. The one would be like this. I'll do the hard part. X of, let's say, theta phi. I'll get rid of the r. I'll do cosine theta, sine phi, sine theta, sine phi. Tell you what, I'll stick three-dimensional here for the moment because I don't want to. See, the four-dimensional is more fun though. Oh, here, let me make this four-dimensional. You know how I can make this four-dimensional? There. Now it's four-dimensional. But this is what's called a parameterization, right? So the way this is working is X is a map, right? Although my daughter criticized me, she said, this is an hourglass. I'm like, it's an X. It's a big X. Let me be. And let's let theta go from 0 to 2 pi. And let's let phi go from 0 to pi. All right? And that's the input, right? This is the parameter space. And where's it going to? It's going to, yeah, these 4 things, right? So R4. I'm going to call the thing it's going to S, though. And S is a subset of R4. Let me give this a name. The domain of X, let's call it big D. So what we really have here is X times big D, X of big D is equal to S, right? The surface is the image of the domain of the parameter space under the parameterization. You can literally think of this as a kind of way of taking the set D and kind of like pasting it up in 4 dimensions, right? But it doesn't paste it flat, right? It actually pastes it in a sphere. This is a sphere.
Yeah, it looks similar. I was just thinking there was like a row.
Oh, right. But I set the row equal to 1. So my question then is, if we need letters, right? Like what's our coordinates for R4? Let me propose that we use X, Y, Z, and I don't know, W sounds good to me. So it's X, Y, Z, W space, right? So this is a notation. So the usual R2 we work with, I might write like R2 sub XY if I want to announce, hey, I'm using the XY coordinates on the R2. So this notation tells me I'm using XYZW coordinates on R4. And with respect to that notation, what is S? S is what? Well, it's the XYZW such that what? 0 to 2 pi, 0 No. I'll get you started. X is equal to cosine theta. I mean, there's different ways to answer my question, and you may have been going to the end rather than the beginning, but X is cosine theta sine phi, right? Y is, but that's just this is not the end of the road. I mean, because at the moment, I mean that's not a. I mean, I would say that this is well. These are what are often called the parametric equations, which I think is just horrible. Honestly, a horrible way to think, because I would really much prefer to think about a patch, which is a mapping from the parameter domain to the space. Or I would like to think about a solution set. And the way to characterize a solution set to an equation is to just use the variables for the space, right? So really what I want to do is eliminate the parameters. And the thing is, with these, if you add x squared plus y squared, what do you get? You get a cosine squared theta plus a sine squared theta, and they're both multiplied by what? Sine squared phi, right? So those things squash into just sine squared phi. And this guy, you got cosine phi here, right? So what's x squared plus y squared plus z squared? Right. Yeah, and then we got W equal to 1. And these two, collectively, the solution set to those two equations defines S. Now, to be more careful, the way I like to say it is this. F of x, y, z, w equal to x squared plus y squared plus z squared, comma, w. So this is a function what? F is a mapping from R4 to R2, right? And what is S? It's the inverse image of the point 1, 1 under F. So this is a very different viewpoint than this. So what I'm telling you is we can either describe the surface in 4 dimensions parametrically, right, as the forward image of a patch, or we could describe the surface as the solution set to 2 equations, which we can understand as being the inverse image of a point under this mapping F. So parameterization is a forward image, solution sets as an inverse image. These are 2 different sides of the same coin. These are 2 very different ways of thinking about a surface, right?
Yeah, it makes more sense to me to think of it as the first way,
Mm-hmm.
like parametric equations. That's maybe because I'm just used to it.
Well, yeah, but in some sense, this is really just honestly, this is a shorthand for that, right? But we face the same difficulty in Calc 3, right? Do you parameterize a surface, or do you look at it as a level equation? Level surface, we call it.
No, to understand the curve, I'll put find the points, or graph it.
Graph it. Well, that is a luxury that we cannot afford, because we're in R4. But, well, I don't know. I mean, well, there's an old debate. Hey, do you want to see a sphere, a 3-sphere in R4? Do you know what a 3-sphere is? It would be x squared plus y squared plus z squared plus w squared equal to 1. Do you want to see a picture of it in R4? All right. You ready? Here goes. See, who says you can't graph R4? You just have to project some of the dimensions. No, I mean, this is the problem. Is like R3 is nice because we have visual intuition there still, but we have to develop other ways of doing things. That's part of what we're after in here, actually.
Yeah, if you change the subset of answers, then yeah, I guess it also makes sense as well.
Oh, so anyway, we could take a point, right, on the sphere, and we could calculate the tangent space to it, right? And the way you do that for the parameterization is you just calculate the derivatives with respect to the parameters, and those will give you the velocity vectors of the coordinate curves. You take the span of those, that's your tangent space. In contrast, if you have this way, if you take gradients of these functions, they give you vectors which are actually perpendicular to the tangent space. So like the gradient vectors to these naturally describe the normal space. So normal space is very easy to understand in terms of the equations viewpoint. but the tangent space is most easy to understand if we have like a parameterization of the object. But I think I'm getting way, way too far into the weeds here. I was just trying to, I'm really just, there's like a paragraph I have on page 4, and I just wanted to give some examples to try to give you some sense of what on earth I was talking about there, because I think I've gone too far. So, tell you what, I'll try to make up a homework problem or two that are based on this. Try to make it more concrete for you guys. Okay, so that's on my list of things to give you. I'll try to write the homework in such a way that I guide you through the calculation, so that you're not like floundering, right? You will need to do partial derivatives. You will need to, you might need to figure out how to calculate the perp. We should talk about that. That's a calculation you've done in linear algebra, but you might not have thought about it. So I'm going to resist the temptation to actually like calculate the tangent space to this, because it will eat a half hour of our time, because spheres are actually kind of nasty. You actually plug a point in and do stuff. It's a mess. I don't know. So imagine, if you will, we have a set, all right? Some subset of R4. Maybe it's a sphere, I don't know, whatever it is. And you work it out, and the tangent space to P of that set works out to be the span of, let's say, 1, 1, 2, 3, and 0, 1, 2, 0. Right? And you'll forgive me, I think I have lost my P again. Would you guys mind if I say vectors based at P at the top? Okay, so. All right, so how would you calculate the perp to this? So, let me say it this way. If A, B, C, D is in here, right? Then what? Equals what? Yeah, but those dot products have to be what? If this is vectors in the perpendicular space, what? 0, right? Yeah, exactly. So, what is that problem we're facing? We're facing A plus B plus 2C plus 3D equal to 0, and, well, B plus 2C equal to 0, right? Solve it, yeah, so we have to find, this is a null, find the null space basis problem. You're like, well, I liked what I said before about matrix. I'm not so sure I'm happy about what you said about basis and null space, but no. I don't think we disagree. I'm giving words for it. So we strip off the variables, write the matrix, right? The augmented coefficient matrix. Do row reductions on it until what? Nice, you get nice answers, right? Until you get the reduced row echelon form, right? So if I subtract row 1 from row 2, I get, row 2 from row 1, I should say. So, whatever notation you guys use. But that would give me 1, a 0, a 0, a 3, 0. Of course, writing the last column of zeros is kind of stupid, but oh well. Too late, I did it. And yeah, that's it. That's reduced row echelon form. You know you're in reduced row echelon form when your pivot columns are the standard basis. E1, E2. Now, then, this tells me that what I have is I have A is equal to minus 3D. And this tells me B is equal to minus 2C. And then what you have to do is you take these and you plug them back up into here. And that gives us minus 3D minus 2C, C, and D. Right. And now what we do is, well, we could just leave it like that. We could say all C and D such that this, right? But a nicer way of writing it in the linear algebra way is to pull the C out. And pull the D out and recognize that what we're facing here is a span. See, in other words, I've just calculated the span, that the perp to TPS is in fact the span of 0, minus 2, 1, 0, minus 3, 0, 0, 1. And then at this point in my life, I usually check my answer. So how would we check our answer? Like, is this perpendicular to these two? Yeah. So yeah, I got 1, 2 here and here, right? So having minus 2, 1 makes that be minus 2 plus 2 both times. So we get 0. Hooray. And then the other one, this minus 3, 0, 0, 1, and go, it makes that go away, and that one's 0. And half the time when I do these, after I get through this calculation and get to the end, I go, I could have guessed that anyway. A lot of times, like, sometimes you can guess, right? And you got to keep in mind the context, right? So if we're in 4 dimensions and you're trying to find the perpendicular space to a 2-dimensional space, if you can find 2 linearly independent vectors which have dot products which are 0 with your given spanning set, you're done. You don't have to do this calculation if you can guess it. But if you can't guess it, it's a pretty standard calculation. But I think it's one I should show you because you probably haven't seen it in a while. And I bet when you did this in linear algebra, you didn't think about it as a solution to this problem, right? It was just like part of your, this is how we reduce matrices, right? And this is, you find the basis for the null space, maybe is a thing you did. But you cheat in physics? Really? Oh, the circuits?
No, I'm doing circuits now. I'm in physics too now, but no, like if you had 2 objects like crashing into each other, you just set all the variables that you need to find, and then just review row echelon format instead of like plugging this thing into this thing or this thing into this thing.
So you just let the calculator do the work rather than.
My professor was cool with it because he said it was right.
So you have like a calculator that would do the row reductions, or?
No, I just did it by hand.
Oh, wow.
Just messing something up. It's so fast trying to figure out what it goes in. It was like you had an object on a desk and you had 2 objects hanging off the desk.
Mm-hmm.
And like each one had a mass and you had to figure out something.
Cool. All right. Okay, so now that we have some sense of what a tangent space is, right? I mean, you see that we have the totality of all possible tangent vectors at a point to play with, but if we're looking at an object which isn't all of Rn, then like the tangent space to it is going to be smaller. It's going to be like some subset of all those vectors. And in that case, we can ask the question, what else is there, right? And what else is there is the normal space. Now, in here we're going to study curves for a little bit, and then we're going to study surfaces for a while, all right? And for the most part, we're going to be in R3. All right, so like my notes are more general at the start, and I've got some somewhat abstract stuff up front. But once we get past this little road bump of me being abstract, we're going to be in R3, basically doing Calc 3 on steroids for a while. Okay? But I wanted us to take a step back and to try to understand how we might think about these things in a more abstract way. Now, maybe that's the wrong approach. You know, I'm still working on things here, but so the next question is, so all right, so we don't just talk about tangent vectors to a point, right? What do we talk about in Calculus 3 and physics? We talk about vector fields, right? And so how would you describe a vector field? What's a vector field? A space which vectors can move freely? Let's see, how about this? What's a vector field on a curve? Like if we want to picture it, what would a vector field on a curve look like? Yeah. Yeah, I mean, I guess that's the thing is the vector field on a curve, right? If it's going to be in the tangent space to the curve or the tangent bundle to the curve, if you want to talk about that, those are just going to line up with the curve, right? But we do think about other things, right? Like the vector doesn't have to point along the curve. It could point perpendicular. It could point other directions, right? It would still be a vector field on a curve, right? But the point is, for each p in the curve, we assign PV in TP Rn. Whatever dimension the curve is sitting in, right? That's what a vector field is. It's an assignment of a vector at each point along the curve. If your surface, whatever it looks like, is sitting in Rn, what's the vector field to the surface? I mean, I can kind of sketch it. I mean, the point is the vectors are anchored on the surface, right? And there are special vector fields to the surface which are tangent to the surface, right? Yeah. That's possible, but that's not all we could think about. We could also think about, like, in Calc 3, we have the normal vector field, right? Which is kind of like totally untangential, right? It's like away from the tangent. It's normal to the tangent plane, in fact, the normal field. But it's almost the same thing, right? Except for each what? P in the surface, we assign PV over here, right? And this song remains the same, right? If we had a different object, the vector field on that object is just an assignment of the vector field at each point in the object. And you could talk about the bundle map pi from the tangent space to Rn, the tangent bundle to Rn. So this map